Question 1, we're looking at standing waves. A piece of string is held between finger and thumb and allowed to hang vertically downwards. That's our diagram just there. When the string is rolled between the finger and thumb, a wave is sent down the string and a standing wave is set up. So before I even get into the question, the first question, this rolling between the finger and thumb, I don't exactly know what they mean by that. I think that it's a little bit like rolling a pen between finger and thumb as you sort of idly wait, and that this kind of sends the wave. Either way, it doesn't matter, but the thing that matters is you've got a wave being sent down the string, and a standing wave is set up inside that string. So part 1 is describe how waves travelling down the string result in a standing wave being set up. So first of all, we need to know what a standing wave is. And we would look at the definition, okay, define it, definition, and when we do that we can then see if those parts of the definition are present here, and that'll kind of explain what's going on. So first of all, standing wave is two waves, okay, travelling in opposite directions, one going that way, one going that way in the medium, and they add together to produce the standing wave, and they have to both be the same frequency, and the frequency is dependent upon the length of the string and so forth. But I think that there are two waves is the part that we need to approach here. So two waves travelling one in each direction. We know that there is a wave travelling down the string. So we want to know, where does the wave come from travelling up the string to produce the standing wave for the addition? And the answer is that there is a reflection off the bottom. Even though it is not a fixed end, you still get reflection. There is a reflected wave which adds to the first wave. So that's what that question's getting at. Part 2, we have to explain why the standing wave will have a node at the top. It's a node at the top, but not at the bottom. So there are two things there. We need to explain why there's a node at the top and not at the bottom. First of all, we need to know what a node is. Node is a fixed point, okay, of 0 amplitude. That means the wave can't move there. And straight away we can see that if the wave can't move at that point, at the top the fingers are fixed, and at the bottom the string is loose. Loose string, and so therefore you can't have a node at the bottom because it's loose, but you can have a node at the top because it's fixed. In fact, you have to have a node at the top and no node at the bottom. The length of the string below the point that is held by the finger and thumb is 12 centimeters. Looks like important information, so I'm just going to circle that or highlight that. B, if the speed of the wave in the string is 2.5 meters per second, calculate the frequency. So we're trying to find the frequency of the standing wave that has two nodes, including the node at the top. Okay, so a good approach to this is first of all to work backwards. Look at the wave that has two nodes. You can draw a sketch of it. You might have seen the diagrams that look something like this, and that's for in pipes particularly. But there's one node there, there is another node there, and this would represent an open end. So this is the waveform that has two nodes, including the node at the top. Now what we need to know is the frequency of that, and we're given the speed, 2.5 meters per second, and we know that the length of this is 12 centimeters from there to there. Now it's important also to note that this is not a full wave. A full wave would continue down to here, and that is one complete wave. So 12 centimeters plus this little bit will give us the wavelength. So wavelength is that 12 plus a bit. Okay, and we can look at this, divide this into sections, and we can see that there are 3 bits in the 12 centimeters and 1 bit in that remaining section. So that means the full wavelength will be 4 times one of those thirds of the 12. So the wavelength is going to be 4 times one of those little bits, which is 12 divided by 3, because we've got 12 centimeters for 3 bits, we want the length for 1 bit, so it's 4 times 12 over 3, excuse me, which gives us 16, is that right? 12 divided by 3 is 4, 4 times 4 is 16, so 16 centimeters. Remember, we've got centimeters here. When we're dealing with our frequency calculation, we're going to need to convert to SI units, because this part here is not so much a calculation as an awareness of what's going on, sort of a common sense approach to the waveform. But anyway, we know V equals F lambda. We're trying to find the frequency now. Frequency equals V over lambda. The velocity is 2.5 and the wavelength is 16 centimeters, which is 0.16 meters. So we can plug that in and perform our calculations to get the frequency of 16 hertz. 16 hertz, that's 16 cycles per second. It's really nice. C, and the last question in this question, we've got the standing wave that has the lowest possible frequency is called the first harmonic, or often called the fundamental. In the string, the next lowest frequency standing wave is called the third harmonic, because it has 3 times the frequency of the first harmonic. Calculate the frequency that is twice the frequency of the first harmonic, and discuss why the string cannot resonate at the second harmonic frequency. Well, we found the frequency of the what do we call it? The third harmonic up the top. It's okay. Stepping back, because we could very easily confuse ourselves here. With the string that we have, where we've got a node and an open end at one end, we could have the following. We can have that, which would be the first or the fundamental, first harmonic. The second harmonic is a non-existent in this case. It doesn't work with us because you need nodes at either end to get it. But the next thing that we can have available is the one that we had up there, which was with 2 nodes, and that's actually the third harmonic. So we calculated the frequency for the third harmonic above, 16 hertz, which was actually about 15 point something or other, but we'll just put that down here, that was about 16 hertz. If we want to go back up to the first harmonic, because I just want to explain before we get into that, well, you divide by 3 anyway, so you go 16 divided by 3 to find that frequency, and then you'd just take that and you'd multiply it by 2 to get the frequency of the second harmonic. So it's 5.3, which will give you 10.6 thereabouts for the frequency of the second harmonic. I'll just put that in there anyway. 10.6-ish. You're rounding, you should use unrounded values, and that's hertz. You should use unrounded values to that. But anyway, going back to our original boggle, why did it skip out the second harmonic? That's what we want to know. We did talk about the nodes and why that is, but you'll notice that this is the wave shape that can fit in. For the second harmonic, it said that it would double that. But if we doubled that, we would need a node at either end, and there's not available a node at either end, so we can't have that. That's why we jump straight to this one, because it's the next form that'll fit in with a node at one end and an open end at the other, and it has to form its own little node in to create that waveform. Okay, so that's why that is. Anyway, going back to the actual question and what they're asking us to calculate and find out. So it's obviously a slightly complex question, so we should read it a number of times to check. Standing wave that has the lowest possible frequency is called the first harmonic. We've dealt with that, often called the fundamental. In the string, the next last frequency standing wave is called the third harmonic. So that's in the string, not in all cases, just in the string, because there's 3 times the frequency of the first harmonic. And we can see there the wavelength, that's one wavelength there, or one section of the wave. The wavelength's actually 4 times that. But then this one over here, if In fact, let's write that. 4 times L is the wavelength here. This one, we've got 3/4 of the wavelength is sitting in there. So it'll be, we'd have to add on that extra third, so it would be actually be 4/3 of the wavelength inside there. 4/3 times L, sorry, to get us to the full wavelength. Anyway, so you'll see that as the wavelength is clearly decreasing, the frequency has to increase from our V equals F lambda. So as the wavelength is decreasing, the frequency has to increase. So that's why doubling, or in this case we've divided by 3 for the wavelength, so I've had to multiply times 3 the frequency to get the same velocity, which can't change in a medium unless you warm up the instrument if it's an air one or something. But anyway, so in this string, the next last frequency, standing wave, is called the third harmonic because there's the third times the frequency. Calculate the frequency that's twice the frequency of the first harmonic. Yes, we've done that. That's our 10.6-ish. And discuss why the string cannot resonate at the second harmonic frequency. I think we've done that very well. It's because of the placement of the nodes and the open ends and all that kind of stuff. So, very good. Just double checking there. That was a little bit long-winded at the end. We had to make sure we'd answered the question properly, as you should do in your exam. And if you ever get confused and confugled and mixed up all over the place, just go back and start the question again. Better that you get what you get right, what you do have time to complete, better to get that right than to do a whole lot, rush through and not get a particularly good result for most of them.